So can we get started? Okay, good. So, okay, good. Thanks for coming today. It's my pleasure to have Dr. Yu-Fang Chen from Academy Sinica to visit us to give a talk over automata learning. So Dr. Yu-Fang Chen is, Academy Sinica is similar to Max Planck Institute in Germany, which means that he only needs to do research without teaching. So he's now an associate fellow, which is equivalent to associate professor in Academy Sinica. And he's very well known for his work in automata learning, and I just leave the time for him to give a talk.
Okay, thanks, Zihong. So, as Zihong says, I come from Academy Sinica. It's really a non-profit organization. We make a group profit. And so this will be about automata learning, which is a way to automatically infer models from black box systems. So models, they are good in the prediction and analysis of the behavior of complex systems. Forms of models can be many things. For example, it can be a formula. But today we will focus on models in the form of finite state machine or automata. I'm not so sure if everyone here is familiar with automata or finite state machine. Okay, good. So I'll begin with a very simple example. Again, the coffee machine. So you have two buttons, like to get coffee and tea, and you can insert either €5 or €10, and you have a button to return money. So the state machine will be like this, will look like this. You can, for example, insert €5, and coffee. This is the validation. And so how to construct this model on a coffee machine? Of course, you can read the menu very carefully and then construct it manually. Or you can do experiment, and then there's an approach to, let's say, infer from the experiment you have done. The state machine. That's what I will cover today. So, for example, experiment will be like this. For example, it's 10, 5, and coffee is a valid behavior. If you insert €10, €5, and then push the coffee button, then you get the coffee. This is a valid behavior. But if you push insert €10, and then coffee, you get nothing. If this is the design of a coffee, of course it's very strange. Okay, so besides a way to automatically infer the basic finite state automata, today I will also cover two kind of more advanced model. One is the so-called multiplicity automata. For finite automata, it can be viewed as a mapping from strings to Boolean values, whether a string is in the set or not. Multiplicity automata, it's very similar. It's also a state machine, but it's a mapping from strings to a rational number, which we believe can be used to model more like interesting properties. For example, you can map a sequence of behavior to its power consumption, execution time, or heat generation, etc. Maybe it can be related to your project. Another thing I'll try to cover today is learning algorithm for Boolean automata. So for finite automata, it's mapping from finite strings to Boolean values. But for some system, they will never terminate. In this kind of system, its behavior will be like execute something. For example, in ATM machine, maybe I push some button, and then I get my cash, and user return to the state. The waiting for the next user. The ATM machine will never stop. For this kind of system, we use the so-called Boolean automata to model it, the non-terminating system. So this will be covered today also. So I'll begin with the basic LO star and algorithm. If it is too simple, just let me know. I can do it quicker. So the LO star algorithm is actually the algorithm used by in the CACM article. It's first proposed by Dan Algren in 1987, and then improved by Rivest in 1993. Its assumption is that there assumes a teacher who knows target regular language, and it can answer queries of two types. A membership query asks whether a string belongs to a target set or not. It can be a sequence of, let's say, insert €5, €10, and coffee, this kind of sequence. And you answer whether it should be a valid behavior or not. And the teacher should also be able to answer equivalence query given a conjectural deterministic finite state automata, whether the language of this automata is equivalent to what the teacher has in mind, whether this is the correct model. This is a bit difficult to realize. I will show you how to do this step later.
So maybe try to rephrase it this way. So if we think of, for example, just want to give use an example, say that when we're talking about autonomous driving, then that means that maybe the membership query means that whether for a certain type of driving patterns, for example, I accelerate and then go right and then overtake and merge left. This is somehow like a string of behavior patterns, and then this can be considered as a membership query. And then equivalence query should be somehow like to check whether the machine learning algorithm equals to the automata.
Whether the machine, the brake box machine, for example, your car, whether this automata is a real model. It can be checked by the manually, or maybe you have some conformance testing or some kind of statistical testing. I should explain that part later.
I see.
But yeah, thanks. So, given a teacher like this, the algorithm is guaranteed to learn a model that's really like equivalent to like what the teacher has in mind. That's what the algorithm can do. So the basic theory behind the algorithm is the so-called neural theory, the automata. So it says, it defines an equivalence relation. It says that the two words x, y are equivalent if they cannot be distinguished by any suffixes. For example, for any that in sigma star, if x that in L, then y x y. Sorry, this should be the that. Then x. Oh, sorry. This should be y z. So I hope this will not confuse you. This should be y z, meaning that x y cannot be distinguished by any suffix. So the equivalence class is defined by this relation actually corresponds to the state of the minimum deterministic finite state automata related to L. And it is sufficient so for given two states that given two strings belong to two different states in the minimum DFA, it is sufficient to find a string to distinguish them. That is, let me try to rephrase it. So if two strings x, y, they belong to two different states in a DFA, it must be a case that you can find a word such that you can find a word that such that the x that is not in L and y that is in L, or vice versa. You can find a suffix to distinguish them. And in fact, you don't need to try all words in sigma star. You need only, let's say, if you have n state, you only need n-1 suffixes to find out all possible states in the minimum DFA. That's so this is finding this finite set of sigma star is the object of the star learning algorithm. To be more concrete, I will give you a very concrete example. So assuming that the teacher knows this, the language the teacher knows is this AB plus AAB star. And the learning algorithm will try to find out the states related to this regular language. So it will begin with this data structure like this. So there must be another page. So this part, it will create a table like this. This also appears in the video. So this part is the finite set of suffixes discovered by the learning algorithm. And these are the states discovered so far. And these are the next state. These are for the next state. And we put true in the table if the concatenation of the state with this suffix is in the language. For example, this lambda b, lambda concatenated with b, which is b. This is false because b is not in the target radio language. B is not here. So, initially the table will look like this. So we have lambda as the initial state, and we want to check what will be the next state of lambda, assuming that the alphabet symbol is just A and B. So this is the initial table, and we fill in the table by posing membership queries. So in this case, okay, lambda is in the language, so we have true there. A is not in the language, so we have false here. B is not in the language, so we have false here. So basically what we are doing is that we want to check what will be the next state of lambda after taking the symbol A. And here, because after attaching lambda as a suffix, lambda is an accepting state, but A is not. So we know that lambda and A cannot be the same state. Because the empty string can distinguish these two states. So we know that lambda A should be a new state. So we need to extend the table like this. Now we have two states, lambda and A. They are two different states because they can be distinguished by lambda. And then we check the next state of A. So we also put AA and AB here. Again, we fill in the table using membership queries. Fill in the table using a very strange animation. Sorry. Let me try to see. Here. Okay, that's good. So fill in the table here. Also, we fill in the table by posing membership queries. AA is not in the language, but AB is in the language. So now it's good. And in this case, we call that the table is closed because all the all the rows belong to this part. They have an equivalent row here. So from this closed table, we can construct automata like this. From this closed table, I can construct automata in this way. So we have two states, lambda and A. Lambda and A. Lambda is accepting because after concatenated with empty string, it is true, so it is an accepting state. And A is not an accepting state, so I have these two states. So from lambda, take the transition A, I should go to the state A. From lambda, take the transition B, I should go to the state B, but in this table, A and AB, they cannot be distinguished by any suffixes here. So I believe A and B, they are the same states. So from lambda, taking B, I will also go to A. Because lambda, A and B are the same state now. From A, take a transition A, I should go to AA, but now AA and A are the same state. So I will have a self-group here. And from A, take B, I will go to lambda because AB and lambda, now I believe they are the same state. So that's the first step of learning algorithm. In this step, after I have a conjectural automata, I will pose the so-called equivalence query. Ask the teacher whether this is your model. If not, the teacher should give me a concrete example. BB. So BB is a string in my model. BB is accepted. But BB is not in the target language. So this is the so-called concrete example. This can be, let's say, given manually, or you have some kind of testing to give this kind of answer. And there's a theory that if from a concrete example, there must be a suffix of a concrete example. If I add the suffix of a concrete example and use it as a new experiment, then I can find at least one more state. In this case, the suffix is B. If I add B to the table, I can find at least one more state. So here it is. If I add B here, so I will find that the A and B, they should not be the same state. Because if I concat A with B, it is in the language here. AB is in the language, BB is not. So A and B should be two different states. So I discovered one more state, and I need to also check the next state of B. So I have BA and BB here. And again, I fill in the table using membership queries here. And this table is closed because every row here, I have an equivalent row here. FT is here, TF is here, FF is here. So from across the table, I can again construct another conjectural automaton. So I have three states, lambda, A, and B. From lambda, take A, I should go to A, and from lambda, take B, I should go to B. From A, taking A, I should go to AA, and now A and A are the same state, so I have a self-loop here. So I can construct automaton in the same way, in this way, and pose another equivalence query. In this case, I get another concrete example. This is still not true, because AAB is not in the language, but it is accepted by my automata. Say B is accepted, but it's not in the language. So I still get another concrete example. In this case, I find out that AB is suffix that then I can, if I add AB, the suffix AB to a table, then I can find one more state. So the way to find out the suffix is I can do either some kind of membership. I can do a few membership queries, but basically I will kind of cover this part in the talk. But basically, at least what you can do is that you add all suffixes of this example to the experiment. If you do so, then you are guaranteed to find one more state. Also, the complexity will be worse. But this is what you can do at least. You add all suffixes of these words to the experiment. So if you add AB, then you find a new state AA, and then you fill out all the tables, and this time you get the correct automata. And why algorithm is correct? Because there's a guarantee that for each equivalence query, if your conjecture is not correct, then for each equivalence query, if your conjecture automata is not correct, you can get one more example, and from the one concrete example, from a concrete example, we are guaranteed to discover at least one more state, and the number of states discovered will not be larger than the equivalence classes defined by the Myhill neural converts, because we identify two states here only when they can be distinguished by some suffixes. And according to Myhill neural theory, they cannot be equivalent to the same equivalence class of the Myhill neural theory, because they can be distinguished by suffixes. So if the minimum automata recognize the language L has n states, we can guarantee to converge to the automata using at most a -1 query. And for membership query, we need at most this number to fill in the table. And this part is actually for extracting suffixes. So for each concrete example, assuming that the length of the concrete example is m, we can posing log n, basically perform a binary search using membership queries to find the suffixes that when we add the suffix here, we can find one more state. That's basically the idea of the learning algorithm. So far so good. So this is the basic version of the automata learning algorithm, and then I will try to cover another version which is more efficient. So the previous version they used a table structure to find out whether two strings belong to different states. And actually it's inefficient because for example, here, it is enough, like B, it is enough that using B to distinguish that the lambda and A are two different states. But again, actually we tried like more than this. We also tried to truncate, to attach AB to lambda and A, also try to attach lambda to AB and A. These are actually not necessary to distinguish that lambda and A are the same state. So the idea of the tree-based algorithm is that we just find, we don't do all, like, we don't try to like fill in all the cells in the table. Instead, we only find the necessary part. So that's the basic idea. So it's use a tree structure like this. So these are the experiments that we have. And the tree leaf are the node identified. So in order to say that lambda and 1, 1, 1, 0, they are two different states, it's enough to using lambda, so we will not try the 1. So I will go into detail. So at the beginning, it's begin with it's pose and check whether empty string is in the language or not. If it is, then it creates an automata accept everything. Otherwise, it creates an automata reject everything. So we get the first example. In this case, it's A, because A is not in the target language, but it is here. And using the same trick, we can we know that because A is not in the language, but lambda is, so we know that empty string is a suffix that can distinguish A and lambda. So this is our initial classification tree. And from the classification tree, we can construct a conjectural automata already. So we have two states, lambda and A. And from lambda, if we take B, then we will go to the left branch of this tree, because B is not B concatenated with lambda is B. It's not in the language. So in this case, we will say that B and A they are the same state because they go to the same node. So we will have lambda. After take B, we go to here. And also from A, if I take A, so I will go to also from A, after I take A, I will go to itself because it's go to the same branch.
So you just modify the way you are storing that information, right? But the automata you learn is the same?
Okay. Sometimes they can be different.
They can be different.
But in this case, it's the same. Okay. And I don't really store like the query result here. I only like do extract or membership query in order to when I construct this automata. So I only store this thing. And from the example of BB, in this case, I know that B is a new string to distinguish with a new state. In fact, the B can, if I add B, what can happen is that I will know that the AB and BB, they have different query results. Because AB is here, but BB is not. So I will replace this node with B, like this. So, and from B, if from B I can distinguish B and A that belong to two different states. So using a similar way I can discover new states. So from this I can construct another conjectural automata. So in order to establish transitions I need to do some membership queries.
So you mentioned that this is more efficient.
Yes.
I guess there are, I see at least two potential reasons. One is because you store less stuff in a tree than in a table.
Yeah.
And the other because doing the queries in the tree is faster than doing the queries in the table, right? Or not?
Sorry.
Doing the queries.
The second point, what's this?
Yes, doing the queries on the tree is faster than doing the queries on the table.
Let me think. Not necessarily. Because, I mean, the number of queries you mean, or to store the information?
So I'm trying to see,
yeah.
So you mentioned that this version of the algorithm was better?
Yeah.
I'm trying to see why. So one potential
I think
is
the
storage.
the reason.
It's for the storage.
Because to upgrade the data structure here takes very little time.
Okay.
If you can see, that's what you are thinking, yeah, it is. it is some factor, but it's minor. The main reason is it can reduce the number of equivalence queries in practice. Complexity-wise, actually, it's worse.
Okay.
Because the tree can, in the worst case, the tree can be very unbalanced. When it is very unbalanced, it's worse, but it happens very rarely. So by doing, I will not look in like the detail of our reason. So basically, just show you like there are two different versions. And this version, the table-based version, they use more membership queries. When you implement these algorithms, actually, what happens is that you need to really combine these algorithms with the breakbox system you are going to analyze. For example, maybe you need to connect this with your car, maybe a simulator of your car. So for each membership query, you need to run the car. So it takes some time. So in my experience, to learn an automata of, let's say, 1,000 states, you need even tree-based algorithm. You need a few thousands of membership queries. It can be even worse. And for the kind of case that if you have thousands of states, I can, let's say, I managed to learn it only for a breakbox system that is a program. So membership query can be answered very, very quickly. Basically, I just run a program in the same computer. Any other factors like you need to go through network will slow it down. Yeah. So, and actually there are publicly available libraries. They are very mature already. So these two tools, I recommend these two tools for finite state automata learning. And in the CLCM article, you can find that it can be used in many applications, basically some kind of regression test. You use it to infer a model and check whether the model violates your property. And if we find some trace that violate the property in the model, you can check whether it's really a real behavior of your system. If it is a behavior in your system, then you find a real problem. If not, then you can use the trace to refine your model. So that's the basic strategy. And it can be used to invert the models of different kinds of systems. We have tried one particular case. We use it to infer a model of a program. So the important thing is that what should be the alphabet symbol in your program, in your model. It can be different things. For example, it can be the decisions made in your program. For example, this means that at the first decision point, maybe it's an if-else branch or the while loop. You go to a true branch, and then you go to a false branch, and true. It can be a decision model. Or it can be a code sequence like foo, ba, ba. Or it can be any label that you have. And to check whether this is a valid sequence, you need to either run some kind of solvers, an SNT solver, or to answer this kind of query in order to get a model or a program. And for equivalence queries, of course, it's very difficult. So if you can answer the query very exactly, then you can get. There's a guarantee that you can get precise model. But in reality, this is very difficult. So there are a few possible ways. One is to so-called back learning. So instead of do real equivalence query, you sample according to a distribution that obtained by previous user behavior, maybe some log, and then your guarantee will be statistical guarantee instead of exact guarantee according to this distribution. Say in the following form. If you sample according to this past user behavior, the chance that you find a difference in your model and the system is lower than some epsilon. Epsilon is a parameter that you can choose. The lower the epsilon is, the more queries you need to make here. So that's the peg-based thing. And for some system, you can use the so-called component testing. For example, some protocol, they have some like test set. You can run it to see whether the model you found at least satisfies this set of tests. So these are a few possible ways that we can do.
So let me rephrase it this way. So the thing is that, for example, for autonomous driving, when we want to check if the learned model is equivalent to the system, that's black box system, we can never really run equivalence query. So we have to use this. We have to create some samples based on some distributions, and then we are able to still get a probabilistic guarantee over the relations between the learned model and the illusion model.
Okay, maybe you have some log file
Okay.
or some kind of historical user habit.
Good.
Yeah, so there's some possible ways. So I finished the first part, the finite atomic learning part. So I will go to the quantitative analysis part, how to infer multiplicity automata. Basically, it's a mapping from string to a rational number, which this is the part actually Zhifeng is interested in. But I will not go to the algorithm part. I will only show you what is a multiplicity automata and what the structure of the learning algorithm is and the tool link to tool. So you can try it. So this is a multiplicity automata, and it's actually the language of it's a mapping from a word to a rational number. So given a word like this AA, BBA, so how to compute the output corresponding to this word. So it consists of two steps. First is that I check all, because it can be non-deterministic, so you can have multiple rungs. So for each rung, first I compute the weight of the rung using multiplication. From the initial state, if I take AA, BBA, I will have A, the weight of A is 2, and A minus 2, B minus 1, B another 1, and A. So I will have the weight 2 times 2. Basically all the way I use multiplication. And at the end, I also multiply the weight of the final state. The weight corresponds to one rung. So in this case, AA, BBA will be mapped to minus 16. And I will sum up the weight of all possible rungs. In this case, it has only one rung. And there can be some other model, for example, this one. Actually, it computes the number of occurrence of A in the string. So for this A, B, AA, I actually have 4 rungs. One is that I all the way do self-loop. So I have 1 times 1 times 1 times 1, and the end I times the weight 0. And anytime I eat A, I have a chance to go to the state on the right. So in this case, the weight of final state will be 1. So I have actually 3 different choices here. So I have 3 rungs with the weight of 1. So every time I hold A here, then I can get the rung with the weight 1. At the end, I sum up the weight over each rung. In this case, I get 3, which is the number of occurrence of A in the model. So, and this weight can be any rational number. It need not to be an integer. So that's the model that we are trying. So, and the scenario is very simple. So it's proposed by many people. The algorithm is proposed by Onishi and also Ben Gardner in 90s. I think they claim that it's a simultaneous, like it's an independent observation. And its scenario is very similar to a star. So it assumes a teacher can answer 2 kinds of queries. Find a value query given a string and return a rational number. Equivalence query, check whether the multiplicity automata is recognize the language of your system, if not giving you concrete example. If one can provide a teacher like this, then the algorithm can infer a multiplicity automata, which is a model of your system. So its user actually is very similar to that structure as a star. So, but I will not go into detail here. I will show you. So actually, this is the implementation of our lab. We implemented in MATLAB. But it's not as mature as the previous tools, because we started this project only 1 year ago to try this kind of learning. We find that we believe it may have some good potential, and we have some good experimental results. But there are, let's say, I must admit that there are like very little examples so far. For example, I can infer a model of a calculator. I have like this. So we have several buttons like from 0 to 9 and the button plus and minus. And from the inferred model, I want to compute the average number and maximum number after K button push in the calculator. So, and I use the pay guarantee, and I only sample word of length, average length 5, and from the inferred model, I compare the average number computed from the inferred model with the result obtained by Bruford's elimination. So I really enumerate all rounds of length 5 and compute the average result. We found that the number obtained by our model is very close to the exact number, even up to length 30, although we only sample strings with the average length 5. So this is, and also the maximum number we obtained is also very close to because the optimal solution will because you push 9 buttons like 5 times if you use input strings length 5, and the maximum number we obtained is very close. And you can imagine that it need not to be just a simple example like a calculator. It can be some kind of more interesting properties like consumption after several button pushes. You just need to be able to answer the queries. And another example we have tried is some kind of scheduling example. So we have alphabet symbol from 0 to 9, and the string is like this, means that in the first time start, a customer arrives and it needs 6 time unit to serve it. And in the second time start, there's no customer arrive. And third, no customer. And in fourth time start, I have a new customer arrive, and he needs 4 time unit to serve. And I want to compute the waiting time using first come first served policy. So given a string like this, I have a very simple program to compute the average waiting time required for this kind of input string. So this is the result. So the result obtained by my model is actually exactly match the result obtained by Bruford's elimination. This is another way one thing to show here is that you can have different tricks to encode the behavior of system into alphabet symbols. So this is also a spatial encoding. And this is a more realistic example. So we want to estimate the average amount of data transmission in a website. So we have this kind of alphabet symbol, H1, H2, H3, which means that the first hyperlink, the second hyperlink, the third hyperlink in the web page. So we go to the HTML file of a web page and to get the HTTP links. And H1 means to click the first link, H2 means to click the second link. And in order to do so, because the number of hyperlink in a website is unknown in advance, so we have extended the algorithm to support adding new symbols at the runtime. So that's some result, but we don't have the result of enumeration because actually to check the number corresponds to one string, like H1, H2, H3, we need to do a lot of requests to a website. Let's say a string of length 10, then we need to do 10 requests to the website. And if we do it too frequently, the website will block our request. That's what happened in reality. So we need to add, let's say, 1 second delay in between each request. And this restricts the number of queries we can make to the system. So in reality, to apply this, we may encounter some difficulties like this. So that's another result. Okay. And at the end, I will also show you some little introduction to the models of non-fermenting systems. This is also, this is more theoretical, I must admit. So if we go back to a coffee machine example, all we have is a finite state machine model like this. So I take symbol 5, 10, and coffee and terminates. That's a finite state model of the machine. Actually, the coffee machine should continue working to continue serving more coffees. It does not really like stop like this. So in order to model the behavior of a coffee machine that non-terminating behavior of coffee machine, the coffee machine should accept behaviors like this, like 5, insert 5, 10, return coin, and other 5. This symbol means that I repeat this behavior infinite many times. I can keep doing this. This is a valid behavior of the system. And a set like this we call it omega regular set. So the model of the combination should become this 5, 10, and I can either do return money or get coffee or tea and go back to the state. And a word is accepted by a machine like this if it has a run that can go through a setting state infinity many times. For example, 5, 10, return money, 5, 5, 5, return money, 5, 5, coffee, etc. As long as the word has a run that can go through this infinity many times. Basically, you can imagine this as the initial condition of the machine. It can be ATM, the default welcome page of an ATM machine. After you do something, you'll go back to a state like this. So this is the symbol, this is the kind of automata. So you can check that all the examples that we mentioned before can be accepted by this model. So we use actually this result. Given a word in this form, U, V, omega. V, this means that begin with the behavior U and then repeatedly doing the behavior V. Given a word like this, if U, V, omega is in L, then I have U $V in the set. $sign is a symbol that is not in the original alphabet symbol. And there's a result that if I do this set, it's a regular set. So one way, actually, we developed the first learning algorithm for this omega regular language. And our intuition is very simple. If this set is regular, why not use L star to learn this set? So this is what we have done in 2008. So what we are doing is very simple. Actually, we use L star to learn the so-called regular image of the omega regular language. So for a string membership query, because what we assume is a teacher that can answer queries about an omega regular language. So it should answer membership queries that in the form of UV omega. But here, L star will only ask membership queries in the form of, let's say, a finite string. So we need to do, actually, our main contribution is to have a translator that translate the queries related to the omega, to the regular image to the omega string. What we are doing for membership query is very simple. We check whether the string is in the form of $V. If it is, then we translate $V to UV omega and ask whether it is in the language. Equivalence query is more involved, but we can also do that. So this is what we have done. And then there are more advanced algorithms, and we have implemented all learning algorithms for omega regular language in this library. It's also like open for public. So that's the end of my talk.